Right now, hurtling through the darkness of space at 110 kilometers per second, a galaxy containing 1 trillion stars is racing toward us. In roughly 4 billion years, give or take, it may collide with our Milky Way in one of the most spectacular cosmic events imaginable. This approaching giant, visible to your naked eye on a dark night as a faint smudge of ancient light, has been watching over Earth for billions of years. The ancient Persians saw it. You can see it tonight. And its story, written across 2.5 million light-years of space, holds secrets about the birth of galaxies, the nature of dark matter, and the ultimate fate of our cosmic home. This is the Andromeda Galaxy, and you're about to discover 100 fascinating facts about our nearest major galactic neighbor. So let us begin this journey slowly, carefully, as we drift across the cosmic distance to our neighboring spiral, exploring the intricate details of a galaxy that mirrors our own, yet holds mysteries all its own. We'll travel through time and space, from ancient observations to modern revelations, from the visible light of 1 trillion stars to the invisible architecture of dark matter that binds them together. This is a story of discovery, of cosmic violence and serene beauty, of the deep past and the distant future. This is the story of Andromeda. Discovery and early observations. On a clear autumn night, far from city lights, you can see it, a faint, elongated blur in the constellation Andromeda. To the naked eye, it appears as nothing more than a dim, ghostly smudge, easily overlooked among the sharper points of stars. Yet this unassuming patch of light represents something extraordinary. An entire galaxy, a vast island universe containing roughly 1 trillion stars, lying 2.54 million light-years from Earth. The earliest recorded observation of the Andromeda Galaxy dates to the year 964 CE, when the Persian astronomer al-Rahman al-Sufi documented it in his Book of Fixed Stars. Al-Sufi, working at the Buyid court in Isfahan, described what he called a small cloud in his comprehensive catalogue of celestial objects. This simple description marked the first written record of a galaxy beyond our own, though al-Sufi could not have known the true nature of what he observed. To him and the scholars of his time, this little cloud was simply another curious feature of the heavens, categorized alongside stars and other nebulous objects, whose nature remained mysterious. For nearly a millennium after al-Sufi's observation, the true identity of this celestial smudge remained unknown. Astronomers in Europe, unaware of al-Sufi's earlier work, rediscovered the object multiple times. In 1612, the German astronomer Simon Marius observed it through one of the earliest telescopes, describing it as resembling the flame of a candle seen through translucent horn. This poetic description captured the object's soft, diffuse appearance, so unlike the sharp points of stars, but offered no insight into its actual nature. Throughout the 1700s and 1800s, as telescopes improved and systematic sky surveys became more common, astronomers catalogued numerous fuzzy, cloud-like objects scattered across the night sky. The French astronomer Charles Messier, hunting for comets in the 1770s, compiled a famous catalogue of objects that might be confused with comets. He wanted to help comet hunters avoid wasting time on these stationary fuzzy patches. The Andromeda object became number 31 in his catalogue, designated Messier 31, or M31, a label that astronomers still use today alongside its new general catalogue designation, NGC 224. At this point in history, astronomers understood that these nebulous objects existed, but fierce debate raged about what they actually were. Some believed they were clouds of gas within our own Milky Way, perhaps regions where new stars were forming. Others suspected they might be something far more exotic, separate island universes, entire galaxies like our own, but vastly distant? This question became one of the great controversies of astronomy, dividing the scientific community and inspiring passionate arguments. The debate reached its zenith in 1920 with the famous Great Debate between astronomers Harlow Shapley and Heber Curtis. Shapley argued that spiral nebulae like Andromeda were relatively small objects within our galaxy, while Curtis championed the island universe hypothesis. Curtis pointed to several compelling pieces of evidence. The dark lanes visible in Andromeda resembled the dust lanes astronomers had identified in the Milky Way. Novae, stellar explosions, appeared in Andromeda, but were consistently fainter than novae elsewhere in the sky, suggesting enormous distance. And the object showed a significant Doppler shift, indicating high velocity that seemed unlikely for objects within our galaxy. Despite Curtis's arguments, the matter remained unsettled until the early 1920s, when a young astronomer named Edwin Hubble made observations that would revolutionize our understanding of the universe. Using the 100-inch Hooker telescope at Mount Wilson Observatory, then the largest and most powerful telescope in the world, Hubble photographed Andromeda and carefully studied the individual stars he could resolve along its outer edges. Among these stars, Hubble identified a particular type called Cepheid variables, stars that pulsate regularly, brightening and dimming over days or weeks. Earlier work by astronomer Henrietta Leavitt had established that Cepheid variables follow a predictable relationship between their pulsation period and their intrinsic brightness. Slower pulsating Cepheids are intrinsically brighter than faster pulsating ones. This period luminosity relationship transformed Cepheids into cosmic measuring sticks. By measuring how long a Cepheid takes to complete one pulsation cycle, astronomers can determine its true brightness. By comparing that true brightness to how bright it appears from Earth, they can calculate its distance. When Hubble applied this technique to the Cepheids in Andromeda, the results were staggering. His calculations indicated that Andromeda lay approximately 900,000 light-years away, far beyond any reasonable estimate of the Milky Way's size. This single measurement settled the Great Debate and fundamentally transformed our conception of the universe. The spiral nebulae were indeed island universes, separate galaxies scattered throughout an almost incomprehensibly vast cosmos. Our Milky Way was not the entirety of creation, but merely one galaxy among countless others. Hubble's initial distance estimate would later be revised upward as astronomers refined their techniques and discovered that there are actually two types of Cepheid variables with different properties. Modern measurements, utilizing not only Cepheids, but also other distance indicators like eclipsing binary stars and the tip of the red giant branch, have established that Andromeda lies approximately 2.54 million light-years from Earth, nearly 3 times farther than Hubble's original estimate, but still remarkably close by cosmic standards. The revelation that Andromeda represented an entire galaxy fundamentally changed astronomy. If this one nearby spiral contained hundreds of billions of stars, what did that imply about the universe as a whole? The cosmos suddenly became vastly larger, vastly more complex, and vastly more populated than anyone had imagined. This shift in understanding ranks among the most profound conceptual revolutions in human history, comparable to the Copernican realization that Earth orbits the Sun, or the recognition that our Sun is merely one ordinary star among billions. Physical characteristics and structure. The Andromeda Galaxy sprawls across the night sky, though most of its extent remains invisible to the unaided eye. If you could see the entire galaxy, not just its bright core, but its full halo of stars and gas, it would appear more than 6 times the width of the full moon, an immense ghostly spiral dominating the constellation. This apparent size, despite the galaxy's enormous distance, testifies to its true physical dimensions. Measurements indicate that Andromeda spans approximately 220,000 light-years in diameter, making it larger in extent than our Milky Way, which measures roughly 100,000 to 150,000 light-years across. However, recent research has revealed something surprising about these two galactic giants. Despite Andromeda's larger size and greater number of stars, the two galaxies appear to have similar total masses. Both galaxies weigh in at approximately 800 billion solar masses in stars and gas, with total masses, including dark matter, reaching around 1 trillion solar masses. This unexpected parity emerged from studies published in 2018 that reassessed both galaxies' masses using improved techniques. For decades, astronomers had believed Andromeda significantly outweighed the Milky Way, perhaps by 50% or more. The new measurements suggest that earlier estimates may have overestimated Andromeda's dark matter content. The galaxy contains roughly 1 trillion stars, substantially more than the Milky Way's estimated 100 to 400 billion stars. But these stars appear, on average, to be older, less massive, and redder than those in our galaxy. This difference in stellar populations, combined with revised dark matter estimates, brings the two galaxies into closer balance than previously thought. The galaxy's structure reveals the classic architecture of a grand spiral. Like the Milky Way, Andromeda possesses a central bulge, a roughly spherical concentration of old yellowish stars densely packed around the galactic core. This bulge measures approximately 15,000 light-years in radius and contains billions of ancient stars following complex, interweaving orbits. Surrounding the bulge, a flattened disk extends outward, containing both old stars and younger, bluer stars forming in spiral arms. These spiral arms, traced by bright, young stars and glowing clouds of hydrogen gas, wind outward from the central regions in an elegant logarithmic pattern. The arms are not solid structures, but rather density waves, regions where gas and dust temporarily accumulate due to the galaxy's gravitational field and rotation. As material enters these density waves, it compresses, triggering the collapse of gas clouds and the birth of new stars. The brightest, most massive of these newborn stars shine intensely blue and die quickly, so they illuminate the spiral arms where they formed. This process creates the striking spiral pattern visible in photographs of Andromeda. The disk itself rotates, though not as a rigid wheel. Stars closer to the galactic center orbit faster than those farther out, creating differential rotation that winds the spiral arms tighter over time. Based on observed rotation speeds, the disk completes one rotation approximately every 200 to 250 million years at the Sun-equivalent distance from the center, a span of time so vast that our Sun has orbited the Milky Way only about 20 times since its formation 4.6 billion years ago. Observations reveal that Andromeda's disk is not perfectly flat, but warped, with one side tilted slightly upward relative to the average plane, and the other side tilted downward. Such warps are common in spiral galaxies and can result from gravitational interactions with satellite galaxies, from accretion of gas from the intergalactic medium, or from past collisions with smaller galaxies. In Andromeda's case, the warp may indicate past encounters that have disturbed the galaxy's structure. Beyond the visible disk extends a vast spherical halo containing globular clusters, ancient field stars, and enormous quantities of hot, diffuse gas. This halo represents the galaxy's extended structure, reaching hundreds of thousands of light-years from the galactic center. The halo contains some of the galaxy's oldest stars, objects that formed when Andromeda itself was young, as well as the remnants of smaller galaxies that have been captured and torn apart by Andromeda's gravity over billions of years. Within this halo orbit, approximately 450 to 500 globular clusters, dense, spherical collections of hundreds of thousands to millions of stars bound tightly by gravity. These clusters, some containing stars as old as the universe itself, trace Andromeda's gravitational field as they follow elongated orbits that carry them from the outer reaches down through the inner galaxy and back out again. The Milky Way hosts around 150 to 200 globular clusters, making Andromeda's population substantially larger, though this difference may reflect Andromeda's more complex history of merging with other galaxies. The structure we observe today represents billions of years of evolution, a history of star formation, of mergers with smaller galaxies, of gravitational interactions with neighbors, and of the slow accumulation of matter from the surrounding environment. Every feature, from the spiral arms to the warped disk to the stellar streams in the halo, tells part of this story, a narrative that astronomers piece together through careful observation and sophisticated computer modeling. The supermassive black hole. At the very heart of Andromeda lies a supermassive black hole, a gravitational monster containing approximately 100 to 140 million times the mass of our Sun. This invisible giant lurks at the center of a peculiar double nucleus structure that puzzled astronomers for decades after its discovery. When the Hubble Space Telescope first imaged Andromeda's core with unprecedented resolution in 1991, astronomers were surprised to find not one, but two bright concentrations of light near the galaxy's center. These two peaks, separated by about 1.5 parsecs, roughly 5 light-years, seemed to suggest the presence of two nuclei, perhaps even two supermassive black holes. Further observations revealed a more complex picture. The brighter of the two concentrations, designated P1, is offset from the galaxy's true dynamical center, the point around which the galaxy rotates. The fainter concentration, P2, lies at the true center and contains a dense cluster of blue stars called P3. Nested within this star cluster resides the supermassive black hole, designated M31, pronounced M31 star, analogous to Sagittarius A in our own galaxy. This unusual configuration, with the brightest nuclear feature offset from the actual center, requires explanation. Computer simulations suggest a possible history. Perhaps 1 billion or more years ago, another galaxy merged with Andromeda. During this merger, the two galaxies' supermassive black holes spiraled toward each other, eventually coalescing in a violent event that released enormous energy in gravitational waves. The kick from this merger might have displaced the newly combined black hole from the galaxy's center, sending it on an eccentric orbit. As the black hole moved away from the center, it interacted gravitationally with stars in the densely packed nucleus, gradually losing orbital energy and settling back toward the center. The offset bright peak P1 could represent a disk of stars that formed around the black hole during one phase of this oscillation, while P2 marks where the black hole currently resides, having found its way back to the true center. This interpretation remains somewhat speculative, and other scenarios could also explain the observed structure. What is clear, however, is that Andromeda's nucleus has experienced significant dynamical activity in its past, activity that has shaped the current configuration we observe. The black hole itself, despite its enormous mass, is remarkably quiet. Unlike the supermassive black holes at the centers of active galaxies, which can outshine their entire host galaxy as they consume vast quantities of matter, M31 emits relatively little radiation. It is classified as a low-luminosity active galactic nucleus, meaning it accretes matter only slowly, radiating mostly in X-rays at modest levels. Observations with the Chandra X-ray Observatory have monitored Andromeda's nucleus for years, revealing that the black hole does occasionally flare, brief episodes when its X-ray emission increases, possibly as clumps of gas fall into it or as magnetic field lines rearrange in the accretion flow. These flares provide glimpses of the black hole's immediate environment and the processes operating near its event horizon. Studies using both space-based and ground-based telescopes have revealed long, spiral filaments of gas and dust feeding toward the black hole from distances of several hundred light-years. These filaments represent the black hole's food supply, material gradually spiraling inward under gravity's influence. The gas does not fall straight in, but forms an accretion disk. A swirling maelstrom of matter that heats up through friction and gravitational compression, radiating energy across the electromagnetic spectrum before finally crossing the event horizon and disappearing forever. The supermassive black hole's mass, roughly 100 to 140 million solar masses, places it in the middle range of such objects. It is substantially more massive than Sagittarius A, the Milky Way's central black hole, which weighs only about 4 million solar masses. Yet it pales in comparison to the true giants, like the 6.5 billion solar mass black hole in the elliptical galaxy M87, recently imaged directly by the Event Horizon Telescope. This mass difference between Andromeda's and the Milky Way's central black holes correlates with differences in the galaxy's bulge masses, supporting a relationship that astronomers have identified. The mass of a galaxy's supermassive black hole appears to correlate with the mass of its central bulge. This correlation suggests a deep connection between the growth of supermassive black holes and the formation of galaxies themselves, a connection that observations consistently support, but that theoretical models still work to fully explain. The black hole's influence extends well beyond its immediate vicinity. Its gravity shapes the orbits of stars within the inner parsec of the galaxy, causing them to move at speeds of hundreds or even thousands of kilometers per second. By measuring these stellar velocities and modeling the gravitational field required to produce them, astronomers can estimate the black hole's mass, even though the black hole itself remains invisible. Looking toward the future, Andromeda's supermassive black hole will play a starring role in one of the cosmos's most dramatic events. If the Milky Way and Andromeda do eventually collide and merge billions of years from now, their two central black holes will spiral together and coalesce. The final moments of this black hole merger would release more energy and gravitational waves than all the stars in both galaxies emit in light over the same period. A cosmic cataclysm of unimaginable power, rippling space-time itself. Dark matter and total mass, most of Andromeda, perhaps 85% of its total mass, remains invisible. This hidden component, called dark matter, neither emits nor absorbs light, interacting with ordinary matter only through gravity. Yet despite its invisibility, dark matter dominates the galaxy's mass budget and shapes its structure in fundamental ways. The evidence for dark matter in Andromeda, as in most galaxies, comes primarily from studying how fast objects orbit the galactic center at various distances. According to Newton's laws, the orbital speed of an object depends on the amount of mass contained within its orbit. For our solar system, where the Sun contains more than 99% of the mass, planets farther from the Sun orbit more slowly. Neptune crawls along compared to speedy Mercury. If galaxies were similar, with most mass concentrated in the visible stars and gas near the center, we would expect rotation speeds to decrease with distance from the galactic core. Instead, observations reveal something different. Measurements of stars and gas clouds' orbital speeds show that rotation velocities remain roughly constant far into the outer reaches of galaxies, even where visible matter becomes sparse. This flat rotation curve implies that significant mass must exist far from the galactic center, mass that we cannot see. In Andromeda, this pattern holds clearly. Astronomers have mapped the galaxy's rotation curve by measuring the Doppler shifts of stars and hydrogen gas at various distances from the center. The velocities peak in the inner regions and then flatten out, remaining at 200 to 250 kilometers per second well into the outer disk and halo. This behavior indicates that dark matter forms an extended halo surrounding the visible galaxy, its gravitational influence keeping outer stars in their rapid orbits. Computer models suggest that this dark matter halo is roughly spherical, extending hundreds of thousands of light-years beyond the visible edge of Andromeda. The exact distribution remains uncertain. Dark matter's invisibility makes precise mapping challenging. But observations of satellite galaxies' orbits, stellar streams, and the galaxy's gravitational lensing of background objects all provide clues to its distribution. Recent estimates, published in 2018, place Andromeda's total mass at approximately 800 billion solar masses within the visible extent of the galaxy, with the total mass, including the extended dark matter halo, reaching around 1 trillion solar masses. Interestingly, these new measurements suggest that previous studies may have overestimated Andromeda's mass. Earlier work, using different techniques and assumptions, had suggested masses as high as 1.5 trillion solar masses, implying that Andromeda significantly outweighed the Milky Way. The 2018 revision came from a novel approach, studying high-velocity stars in Andromeda's halo and calculating the escape velocity, the speed a star would need to break free of the galaxy's gravitational pull. By identifying stars moving at speeds close to escape velocity and modeling the gravitational field required to barely retain them, astronomers derived new mass estimates that brought Andromeda and the Milky Way into closer parity. Both galaxies appear to have similar total masses, despite Andromeda's larger size and greater number of stars. This mass similarity has implications for our understanding of the eventual collision between the two galaxies. Earlier models, assuming Andromeda significantly outmassed the Milky Way, predicted that our galaxy would be largely absorbed into the larger Andromeda. The new mass estimates suggest a more equal pairing, two giants meeting as peers rather than a small galaxy being consumed by a larger one. The nature of dark matter itself remains one of physics's greatest mysteries. We know it exists, the gravitational evidence is overwhelming, but we don't know what it is. Various theoretical candidates have been proposed, from weakly interacting massive particles, WIMPs, to axions to primordial black holes, but despite decades of searching, no experiment has yet directly detected dark matter particles. Studies of Andromeda contribute to this search in several ways. By mapping the distribution of dark matter through gravitational effects, astronomers can test predictions from different dark matter models. Some models predict smooth, uniform halos, others suggest clumpiness or substructure. Precise observations of stellar streams in Andromeda's halo, ribbons of stars torn from disrupted satellite galaxies, can reveal whether dark matter clumps disturb these streams as models predict. Additionally, Andromeda serves as a testing ground for alternative theories of gravity that attempt to explain galactic rotation curves without invoking dark matter. These theories, collectively called modified gravity theories, propose that Newton's and Einstein's laws of gravity require revision on galaxy scales. By comparing predictions from these theories with detailed observations of Andromeda's structure, kinematics, and gravitational effects, astronomers can test whether dark matter is truly necessary or whether modified gravity might explain the observations. So far, observations consistently favor the dark matter interpretation over modified gravity, though the debate continues. The precision and variety of data available for Andromeda, from stellar velocities to satellite orbits to gravitational lensing, provide powerful constraints that any successful theory must satisfy. The dark matter halo extending around Andromeda may already be touching the dark matter halo of our own Milky Way. Although the visible disks of the two galaxies remain 2.5 million light-years apart, their dark matter halos, potentially extending 1,000,000 light-years or more from each galaxy's center, could overlap. If so, we already exist within Andromeda's gravitational influence, just as it exists within ours. Two galaxies bound together by invisible halos of mysterious matter, slowly drawing closer through a dance that began billions of years ago. And stellar populations and star formation within Andromeda's vast expanse, generations of stars tell the story of the galaxy's evolution. Approximately 1 trillion stars populate this galaxy, roughly 2 to 3 times the number in our Milky Way, each contributing its light to the collective glow visible across millions of light-years of space. These stars are not uniform. They span a vast range of ages, masses, colors, and compositions, forming distinct populations that astronomers categorize to understand the galaxy's history. The oldest stars, formed when Andromeda itself was young more than 10 billion years ago, populate the central bulge and the spherical halo. These ancient stars shine with the yellowish or reddish hues of cooler, less massive stars, having long since exhausted any massive, short-lived blue stars that might have formed alongside them. The bulge stars follow complex, interweaving orbits around the galactic center, their motion more random than the orderly rotation characteristic of disk stars. This disordered motion suggests formation during a chaotic early period when Andromeda was still assembling from smaller structures, a time of frequent collisions and mergers that stirred stellar motions into the patterns we observe today. The disk contains a more diverse stellar population. Its inner regions, like the bulge, host primarily older, redder stars. But moving outward, younger populations become increasingly prominent, culminating in the spiral arms, where star formation actively continues today. Here, massive young stars blaze brilliant blue, their intense ultraviolet, radiation ionizing surrounding hydrogen clouds and causing them to glow in characteristic pinkish hues. These H2 regions, clouds of ionized hydrogen gas, serve as stellar nurseries where new stars continue to be born. Current observations suggest that Andromeda forms stars at a rate of approximately 1 solar mass per year, meaning the galaxy creates the equivalent of 1 sun's worth of stellar material annually. This rate is actually somewhat lower than the Milky Way's current star formation rate of roughly 1 to 2 solar masses per year, a difference that appears related to the different amounts of gas available in the two galaxies and their recent histories. Andromeda's star formation rate has varied dramatically over its lifetime. Evidence suggests that roughly 2 to 3 billion years ago, the galaxy experienced a major burst of star formation, a period when stars formed at rates perhaps 10 times higher than today. This starburst appears to correlate with a significant merger event, when another galaxy, perhaps 1/4 Andromeda's mass, collided with and was absorbed by Andromeda. The evidence for this ancient merger comes from several sources. Computer models show that the observed structure of Andromeda's disk, particularly a prominent ring of stars at about 10 kiloparsecs, 32,000 light-years from the center, and the galaxy's extended disk, could be explained by the gravitational disturbances from such a collision. Additionally, studies of stellar ages across Andromeda reveal that large numbers of stars formed during this epoch, consistent with collision-triggered star formation. This ancient merger would have been a violent, spectacular event. As the smaller galaxy plunged into Andromeda, tidal forces would have stripped stars and gas from both galaxies, creating long tails and bridges of material streaming across hundreds of thousands of light-years. The compression of gas during the collision would have triggered intense bursts of star formation, briefly transforming Andromeda into what astronomers call a luminous infrared galaxy, an object radiating enormous power primarily in infrared wavelengths due to dust heated by young stars. Today, the scars of this collision remain visible to those who know how to read them. The 10 kiloparsec ring of stars represents a resonance, a region where stars accumulate due to the gravitational structure established by the merger. The extended warped disk suggests material was scattered to great distances by tidal forces, and the stellar populations across the galaxy preserve a record of when and where stars formed, allowing astronomers to reconstruct the merger's timeline. Star formation continues in Andromeda today, though at a more sedate pace. Gas clouds in the spiral arms, compressed by the density waves moving through the disk, collapse under their own gravity to form new stars. The process begins when a gas cloud, cooled to just tens of degrees above absolute zero and containing enough mass to overcome its internal pressure, begins to contract. As the cloud collapses, it fragments into smaller clumps, each becoming a stellar core. These cores continue contracting and heating until nuclear fusion ignites in their centers, hydrogen atoms fusing into helium and releasing enormous energy that halts the collapse. A star is born. The most massive of these newborn stars burn fiercely but briefly. A star 10 times the sun's mass might shine for only 20 million years, a cosmic eye blink, before exhausting its nuclear fuel and exploding as a supernova. These explosions enrich the interstellar medium with heavy elements forged in the stellar furnace and during the explosion itself. The enriched gas eventually cools and condenses again, forming a new generation of stars slightly richer in heavy elements than their predecessors. This cycle of birth, death, and rebirth has operated throughout Andromeda's history, gradually increasing the metallicity, the abundance of elements heavier than hydrogen and helium, of the galaxy's gas and stars. The oldest stars in the halo, formed from nearly pristine primordial gas, contain less than 1% the sun's metallicity. Stars forming in the disk today, from gas enriched by billions of years of stellar processing, have metallicities similar to or even exceeding the sun's. The distribution of stellar ages and metallicities across Andromeda provides clues to its formation history. The presence of very old, metal-poor stars in the halo suggests that Andromeda, like most large galaxies, assembled through a process called hierarchical assembly. Small structures formed first, then merged to create progressively larger galaxies. The metal-poor halo stars likely formed in small proto-galaxies that later coalesced into Andromeda. Meanwhile, the disk's stellar populations suggest more gradual, continuous star formation punctuated by bursts during merger events. The diversity of ages and compositions creates a complex stellar tapestry, each thread representing a different chapter in Andromeda's 10 billion-year history. The coming collision with the Milky Way of all Andromeda's fascinating properties, perhaps none captures the imagination quite like this. The galaxy is moving toward us, and current evidence suggests a collision may occur in the distant future, though recent research has added considerable uncertainty to this scenario. When astronomers first measured Andromeda's motion in the early 20th century, they discovered something remarkable. Most distant galaxies show red-shifted light, their spectral lines shifted toward longer, redder wavelengths due to the expansion of the universe carrying them away from us. Andromeda, however, shows blue-shifted light, indicating it is moving toward us at approximately 110 kilometers per second. For decades, this approaching motion suggested an inevitable collision. Studies published in 2012 using precise measurements from the Hubble Space Telescope confirmed that Andromeda's sideways motion across the sky is small enough that a direct collision appeared certain. These observations indicated that in approximately 4 to 5 billion years, the two galaxies would collide in one of the most dramatic events in our cosmic neighborhood's future. However, Research published in 2025 has cast new uncertainty on this long-accepted scenario. Sophisticated computer simulations that included not just the Milky Way and Andromeda, but also other members of the local group, particularly the Triangulum Galaxy and the Large Magellanic Cloud, revealed surprising results. When the gravitational influences of these smaller galaxies were properly accounted for, the probability of a Milky Way-Andromeda collision within the next 10 billion years dropped to approximately 50%. This doesn't mean the collision is cancelled. It means we're less certain than we once were. In roughly half of the simulated scenarios, the two galaxies do eventually collide and merge, but this might not occur for 7 to 8 billion years rather than the previously predicted 4 to 5 billion years. In the other half of scenarios, the galaxies experience close encounters but pass by each other, continuing to evolve largely separately for billions of years more. If the collision does occur, the process will unfold over billions of years. The first close approach would see the two galaxies pass through each other, their stars so widely spaced that actual stellar collisions would be extraordinarily rare, perhaps non-existent. However, the tidal forces, differential gravitational pulls across each galaxy, would be dramatic, pulling long streamers of stars out from both galaxies and creating spectacular visual effects for any hypothetical observers on planets in either galaxy. Computer simulations of this collision show that the first passage would be relatively gentle but profoundly disruptive. The orderly spiral arms would begin to tear apart, stars scattered into chaotic orbits. Gas clouds would collide and compress, triggering intense bursts of star formation that would briefly increase both galaxies' brightness. The night sky for any observers would transform from the familiar band of the Milky Way to a panorama of stellar chaos, with Andromeda stretched across the sky and new star-forming regions blazing throughout. After this first passage, gravity would slow the galaxies' recession from each other and eventually reverse it, pulling them back together for a second, more violent encounter. Multiple passages would occur over perhaps 1 billion years, each disrupting the galaxies further, until eventually the two would settle into a single merged galaxy, likely an elliptical galaxy, a smooth, nearly featureless distribution of stars with no clear spiral structure. Astronomers have nicknamed this future merged galaxy Milkomeda, or Milkdromeda, a union of two names for a union of two histories. The merged galaxy would be one of the most massive in the local group, containing the combined mass of both progenitors. The gravitational choreography has already begun in subtle ways. Andromeda's gravity tugs at the Milky Way across the void, influencing the velocities of stars in our galaxy's outer regions. Similarly, our galaxy's gravity reaches across space to Andromeda, creating tidal forces that pull at its structure. These forces, though minuscule compared to the internal gravitational binding of each galaxy, accumulate over billions of years, setting the stage for possible merger. The merger would also affect the supermassive black holes at the centers of both galaxies. As the galactic cores sink toward each other through dynamical friction, the gravitational drag exerted by surrounding matter, the two black holes would form a binary system, orbiting each other at ever-decreasing distances. Eventually, when separated by just a few light hours, gravitational wave emission would become significant, carrying away orbital energy and angular momentum. In the final moments before merger, the black holes would spiral together in a death dance lasting just minutes, releasing more energy in gravitational waves than all the stars in the observable universe emit in light during the same time. This black hole merger would be one of the most energetic events in the local universe, potentially observable by future gravitational wave detectors. The merged black hole would have a mass around 100 to 140 million solar masses from Andromeda's black hole, plus 4 million solar masses from the Milky Way's Sagittarius A, making it one of the more massive black holes in the local universe. For any hypothetical observers on planets orbiting stars caught up in this merger, the night sky would undergo dramatic transformations. Early in the process, Andromeda would appear larger and larger, eventually stretching across a significant portion of the sky. During the closest approaches, the sky would be ablaze with star-forming regions as gas clouds collide and compress, triggering bursts of new stellar birth. The orderly Milky Way band we see today would dissolve into a more chaotic distribution of stars. Yet individual stars and their planets would likely survive unscathed, simply finding themselves in different orbits within the merged galaxy. The story of the coming possible collision transforms Andromeda from a distant object of study into a companion on a potential shared cosmic journey. These two galaxies, born in the early universe, enriched by generations of stars, sculpted by dark matter, may be moving toward a union that would create something entirely new. Whether that collision actually occurs remains uncertain. Recent research reminds us that even predictions billions of years in the future contain considerable ambiguity. But the possibility alone illustrates the dynamic nature of cosmic evolution and connects Andromeda to our own future in the most intimate way. Tidal interactions and disruption. Beyond the possible eventual collision with the Milky Way, Andromeda has experienced numerous gravitational encounters throughout its lifetime that have shaped its current structure and morphology. The tidal interactions between galaxies represent some of the most dramatic and visually spectacular processes in astrophysics, and Andromeda bears the subtle scars of these ancient encounters. Tidal forces arise whenever different parts of an object experience different gravitational pulls. On Earth, we see tidal forces in action through the ocean tides caused by the Moon's gravity. The side of Earth facing the Moon experiences slightly stronger gravity than the far side, creating a stretching effect. On galactic scales, tidal forces become powerful sculptors of structure, capable of pulling long streamers of stars and gas from galaxies during close encounters. Observations of Andromeda reveal several features that suggest past tidal interactions. One of the most intriguing is a giant stellar stream in Andromeda's halo, a long, thin ribbon of stars that wraps around the galaxy. This stream was discovered through deep imaging surveys that revealed faint structures invisible to earlier observations. The stars in this stream are moving coherently, suggesting they were once part of a smaller galaxy or globular cluster that was tidally disrupted by Andromeda's gravity. When a small satellite galaxy approaches a larger galaxy like Andromeda, the differential gravitational forces across the satellite begin to pull it apart. Stars on the near side experience stronger gravity than those on the far side, creating a stretching effect that eventually overcomes the satellite's own gravity. As the satellite is torn apart, its stars are strung out along its orbit, forming a thin stream that gradually spreads around the larger galaxy. These stellar streams serve as archaeological records of Andromeda's past interactions. By studying the positions and velocities of stars in the streams, astronomers can trace backward in time to reconstruct the original satellite galaxy, its mass, orbit, and the timing of its disruption. This detective work reveals that Andromeda has consumed numerous smaller galaxies over billions of years, growing through a process astronomers call hierarchical assembly. The properties of these streams also provide unique tests of dark matter distributions. Since the streams are held together by gravity, and their shapes are determined by the gravitational field they move through, precise measurements of stream morphology can map the distribution of dark matter in Andromeda's halo. Any clumps or variations in the dark matter distribution would cause ripples or gaps in the streams, observable as deviations from smooth, continuous ribbons of stars. Andromeda's disk itself shows signs of past disturbances. The rotation curve, The graph of orbital velocity versus distance from the center displays asymmetries and warps that cannot be explained by a simple, undisturbed disk. These features suggest that Andromeda has experienced gravitational perturbations relatively recently on cosmic timescales, perhaps within the past billion years. One of the most significant discoveries came from detailed mapping of Andromeda's stellar populations in 3 dimensions. These observations revealed that the galaxy's disk is warped, with one side tilted up and the other down relative to the average plane. Such warps are common in disk galaxies and often result from gravitational interactions with satellite galaxies or from the accretion of gas from the intergalactic medium. In Andromeda's case, the warp may be a lingering signature of a past collision with a satellite galaxy, though the exact cause remains a subject of ongoing research. The outermost regions of Andromeda's disk also show a distinct structure sometimes called the Giant Stellar Stream or the Great Southern Stream, a feature that extends far beyond the visible disk and appears to be material tidally stripped from one or more satellite galaxies. This stream contains millions of stars spread across hundreds of thousands of light years, a testament to the violence of past gravitational encounters. Computer simulations have attempted to recreate these observed features by modeling various collision scenarios. These simulations suggest that Andromeda may have experienced a significant merger event in its past, perhaps with a galaxy containing a few billion solar masses, smaller than Andromeda, but substantial enough to leave lasting marks. The timing of this event remains debated, with estimates ranging from 1 to 3 billion years ago. The tidal interactions extend beyond Andromeda's past to its present. The galaxy's satellite galaxies are currently experiencing tidal forces that are gradually stripping away their outer stars. M32, for instance, shows signs of being tidally disturbed, with its outer stellar envelope stripped away by Andromeda's gravity. NGC 205 similarly displays tidal features, suggesting ongoing interaction with its massive neighbor. These ongoing tidal interactions have profound implications for galaxy evolution. They represent a mechanism by which large galaxies grow, accreting smaller companions and integrating their stars into the larger system. This process, called galactic cannibalism, has played a crucial role in building up massive galaxies like Andromeda throughout cosmic history. The study of tidal interactions also reveals the 3-dimensional nature of galaxy dynamics. Unlike the relatively orderly rotation of stars in the disk, tidally stripped material can have highly eccentric orbits, carrying stars far from their original locations. These stars eventually settle into the galaxy's halo, contributing to the roughly spherical distribution of old stars that surrounds the disk. Observations in different wavelengths reveal additional aspects of tidal interactions. Infrared observations, which penetrate dust and highlight cool stars, show extended structures that are invisible in visible light. Radio observations trace neutral hydrogen gas, revealing tidal tails and bridges of gas connecting interacting galaxies. In Andromeda, these multi-wavelength observations have revealed gas features that extend beyond the visible galaxy, possibly remnants of past accretion events. The measurement of stellar ages and chemical compositions in tidally stripped features provides additional constraints on Andromeda's interaction history. Stars formed in small satellite galaxies tend to have different chemical signatures than those formed in large galaxies, reflecting differences in star formation histories and enrichment processes. By identifying these distinct populations in Andromeda's halo and streams, astronomers can identify which stars originated in accreted satellites and which formed in situ within Andromeda itself. Recent surveys have employed sophisticated color magnitude analysis to identify these different populations. They have found that Andromeda's halo contains a mix of stellar populations with varying ages and metallicities, suggesting multiple accretion events spanning billions of years. Some regions of the halo appear dominated by stars from a single large accretion event, while others show evidence of multiple smaller accretions. The future promises even more detailed understanding of tidal interactions in Andromeda. Next-generation telescopes and surveys will map the positions and velocities of millions of individual stars in Andromeda's outer regions, tracing the full three-dimensional structure of stellar streams and tidal features. These observations will provide stringent tests of our models of galaxy formation and dark matter distribution. The story of tidal interactions in Andromeda illustrates the dynamic nature of galaxies. Rather than isolated islands of stars, galaxies exist within a web of gravitational interactions, constantly exchanging matter with their satellites and neighbors. These interactions drive galaxy evolution, trigger star formation, and shape the structures we observe today. Andromeda, with its massive halo satellite system and tidal features, serves as an excellent laboratory for studying these processes in exquisite detail. Chemical composition and metallicity. The chemical composition of stars and gas in Andromeda provides a window into the galaxy's history of star formation, stellar evolution, and chemical enrichment. Astronomers use the term metallicity to describe the abundance of elements heavier than hydrogen and helium, elements that astronomers collectively call metals, regardless of their chemical properties. This metallicity traces the generations of stars that have lived, died, and enriched the interstellar medium with the products of nuclear fusion. When the universe was young, emerging from the Big Bang, it contained almost exclusively hydrogen and helium with trace amounts of lithium. The first stars formed from this primordial gas, containing essentially zero metals. But these early stars were nuclear forges, fusing lighter elements into heavier ones throughout their lifetimes. When they died, some in spectacular supernova explosions, they ejected these newly formed elements into the surrounding gas. Subsequent generations of stars incorporated this enriched material, gradually increasing the metal content of galaxies over cosmic time. In Andromeda, metallicity varies systematically with location and stellar population. The youngest, most recently formed stars in the disk show the highest metallicities, reflecting billions of years of chemical enrichment. These stars, many still surrounded by glowing H2 regions where they were born, contain elements like carbon, nitrogen, oxygen, silicon, and iron in proportions that reflect the cumulative enrichment from all previous generations. The metallicity gradient, the change in metal abundance with distance from the galactic center, provides important clues about Andromeda's formation and evolution. Observations show that metallicity generally decreases with increasing distance from the center, a pattern seen in many spiral galaxies, including our own Milky Way. This gradient suggests that star formation has been more efficient and prolonged in the inner regions, where gas densities are higher and gravitational forces stronger. However, Andromeda's metallicity gradient is not perfectly smooth. Detailed spectroscopic surveys have revealed variations and irregularities that hint at a complex history of gas accretion, mixing, and star formation. Some regions show unexpected enhancements of certain elements, possibly indicating localized bursts of star formation or the accretion of gas with unusual composition. The study of individual elements provides even more detailed insights. Different elements are produced by different processes. Oxygen and neon are primarily made in massive stars and ejected in core collapse supernovae. Iron is largely produced in type Ia supernovae, resulting from white dwarf explosions. Carbon and nitrogen are produced in intermediate mass stars and released during their asymptotic giant branch phase. By measuring the relative abundances of these elements, astronomers can reconstruct the history of different types of stars and supernovae in Andromeda. Spectroscopic observations of individual stars in Andromeda's halo reveal even lower metallicities than in the disk, consistent with these being older stars formed earlier in the galaxy's history. Some halo stars have metallicities just a few % of the Sun's value, indicating they formed when the galaxy was young and relatively unenriched. These ancient stars serve as fossil records of Andromeda's early chemical evolution. The satellite galaxies orbiting Andromeda show distinct chemical signatures. M32, despite being so close to Andromeda, shows somewhat different abundance patterns, reflecting its separate star formation history. NGC 205 displays signatures of recent star formation with correspondingly higher metallicities in its young stellar populations. The dwarf spheroidal satellites tend to have lower metallicities, consistent with their smaller masses and less efficient star formation histories. Gas phase metallicity, the abundance of metals in the interstellar gas rather than in stars, can be measured through spectroscopy of emission lines from H2 regions and diffuse ionized gas. These measurements reveal that Andromeda's gas has been well mixed and enriched to relatively high metallicity, typically ranging from about half to twice the solar value, depending on location. This enriched gas will form the next generation of stars, continuing the cycle of chemical evolution. The pattern of chemical enrichment also provides constraints on gas flows within Andromeda. Gas does not simply stay in place where it is enriched. It can be transported by galactic rotation, by stellar winds and supernova-driven outflows, and by accretion from the intergalactic medium. The observed metallicity distributions require sophisticated models that account for these various processes. One intriguing aspect of Andromeda's chemical evolution involves the role of gas accretion from the circumgalactic medium. Pure closed-box models, which assume galaxies evolve in isolation without gaining or losing gas, cannot fully explain observed metallicity patterns. Instead, evidence suggests that galaxies like Andromeda must accrete fresh gas from their surroundings, gas that is typically lower in metallicity than the enriched gas already in the galaxy. This accretion dilutes the metallicity and sustains star formation over billions of years. Evidence for such accretion comes from several sources. The large reservoir of neutral hydrogen in Andromeda's outer disk, revealed by radio observations, exceeds what would be expected from gas lost by dying stars alone. This extra gas may represent material accreted from the circumgalactic medium or from minor mergers with small gas-rich satellites. The chemical composition of this outer gas, being somewhat lower in metallicity than the inner disk, supports the accretion scenario. The measurement of specific element ratios provides additional diagnostic power. The ratio of alpha elements, like oxygen, neon, magnesium, to iron varies depending on the relative contributions of different supernova types. Core collapse supernova, which explode shortly after massive stars form, produce copious alpha elements but relatively little iron. Type Ia supernova, which occur on longer timescales when white dwarfs accrete matter and explode, produce large amounts of iron. By measuring alpha to iron ratios in different stellar populations, astronomers can constrain the timescales and modes of star formation in Andromeda's history. Studies have found that Andromeda's inner regions show alpha to iron ratios consistent with a mix of supernova types, suggesting prolonged star formation with contributions from both core collapse and type Ia events. The halo stars, particularly the oldest and most metal-poor ones, show enhanced alpha to iron ratios, consistent with formation in an era dominated by core collapse supernovae before type Ia events became significant. Chemical tagging, the practice of identifying groups of stars with similar detailed chemical signatures, has emerged as a powerful technique for understanding galaxy assembly. Stars born in the same cluster or region tend to have nearly identical chemical compositions. By identifying groups of stars in Andromeda with matching chemical fingerprints, astronomers can identify stellar siblings and reconstruct the star clusters and associations where they formed, even if the clusters have since dispersed. This technique has proven particularly valuable for studying Andromeda's halo and stellar streams. Stars in tidal streams, having originated in the same disrupted satellite galaxy, should share common chemical signatures distinct from stars formed in Andromeda itself. Observations have confirmed this expectation, revealing chemically coherent groups of stars in stellar streams that differ from the surrounding halo population. The future of chemical abundance studies in Andromeda looks bright, with several next-generation instruments designed to obtain high-resolution spectra for large numbers of stars. These observations will map the chemical composition of millions of stars across Andromeda, providing unprecedented detail about the galaxy's chemical evolution and assembly history. Combined with precise age determinations and kinematic measurements, this chemical information will paint a comprehensive picture of how Andromeda grew and evolved over cosmic time. The study of chemical composition also connects to broader questions about galaxy evolution across the universe. By comparing Andromeda's chemical properties to those of other galaxies at various distances, and thus various cosmic epochs, astronomers can understand how chemical enrichment proceeds over cosmic history. Andromeda, being nearby and observable in great detail, serves as a benchmark against which more distant galaxies can be compared. The chemical story of Andromeda is ultimately a story of cycles and transformation. Hydrogen gas condenses into stars, which fuse elements in their cores. These stars return enriched material to the interstellar medium through stellar winds and supernova explosions. The enriched gas mixes, cools, and condenses again to form new stars, each generation slightly richer in heavy elements than the last. Over billions of years, this cycle has transformed Andromeda from a galaxy of pure primordial gas into the chemically enriched system we observe today, with metals incorporated into everything from massive stars to the planets that may orbit them. There are variable stars and distance measurements among the billions of stars in Andromeda. Certain special stars serve as cosmic measuring sticks, allowing astronomers to determine distances across vast reaches of space. These variable stars, which change in brightness over regular periods, have proven instrumental in establishing the distance to Andromeda and understanding the scale of the universe. The most famous of these cosmic distance indicators are Cepheid variable stars, named after Delta Cephei, the prototype star in our own galaxy. Cepheids are massive, luminous stars in a particular phase of stellar evolution, pulsating in and out like slowly beating hearts. As a Cepheid expands, its outer layers cool and dim. As it contracts, they heat up and brighten. This cycle repeats with remarkable regularity, with periods ranging from days to months. The crucial discovery, made by Henrietta Leavitt in the early 20th century, was that a Cepheid's period of variation is directly related to its intrinsic luminosity. Brighter Cepheids pulsate more slowly than fainter ones. This period luminosity relationship transformed Cepheids into powerful distance indicators. By measuring a Cepheid's period and apparent brightness, astronomers can calculate how far away it must be to appear as faint as it does. Edwin Hubble's identification of Cepheid variables in Andromeda in 1923–24 revolutionized astronomy. Before this discovery, the nature of spiral nebulae was hotly debated. Were they nearby objects within our galaxy or distant island universes? By measuring the periods and brightnesses of Cepheids in Andromeda and applying the period-luminosity relationship, Hubble determined that Andromeda must lie at a distance of approximately 900,000 light-years far beyond any reasonable estimate of the Milky Way's size. This single measurement settled the debate and expanded the known universe by orders of magnitude. Hubble's initial distance estimate has been refined considerably over the decades. Modern observations, particularly from the Hubble Space Telescope, have identified thousands of Cepheids in Andromeda, providing much more precise measurements. The current best estimate places Andromeda at approximately 2.54 million light-years, nearly 3 times Hubble's original estimate. This revision came not from errors in Hubble's observations, but from improved calibration of the Cepheid period-luminosity relationship and recognition that there are 2 types of Cepheids, classical Cepheids and type Cepheids, with different properties. The observation of Cepheids in Andromeda requires sophisticated techniques. Even though Cepheids are among the brightest stars, their individual images at Andromeda's distance are easily confused with those of neighboring stars, especially in the crowded inner regions of the galaxy. The Hubble Space Telescope's sharp imaging capabilities proved essential for resolving individual Cepheids and tracking their brightness variations over multiple cycles. These observations must account for several effects that can influence apparent brightness. Interstellar dust along the line of sight absorbs and scatters starlight, making objects appear fainter and redder than they actually are. Astronomers must carefully measure and correct for this extinction by observing Cepheids in multiple wavelengths and using the differential extinction at different colors to estimate the total absorption. Infrared observations prove particularly valuable since dust affects infrared light less than visible light. The metallicity of Cepheids, their content of elements heavier than helium, also influences their pulsation properties and luminosities. Cepheids in metal-rich environments pulsate slightly differently than those in metal-poor regions, requiring small corrections to the period-luminosity relationship. Studies of Cepheids in Andromeda, combined with spectroscopic measurements of their chemical compositions, have helped refine these metallicity corrections. Beyond Cepheids, Andromeda hosts other types of variable stars, useful for distance measurements and astrophysical studies. RR Lyrae variables, for instance, are older, less massive stars that also pulsate regularly. These stars are found predominantly in globular clusters and the galactic halo. While less luminous than Cepheids, RR Lyrae stars have the advantage of being standard candles. All RR Lyrae stars have roughly the same intrinsic luminosity, making them excellent distance indicators even without measuring periods. Surveys of Andromeda have identified thousands of RR Lyrae stars, particularly in the halo and globular clusters. These observations have provided independent distance estimates that agree well with those from Cepheids, increasing confidence in our understanding of Andromeda's distance. The RR Lyrae stars also trace the structure of Andromeda's halo and reveal the extent of old stellar populations far from the galactic disk. Eclipsing binary stars provide another independent distance measurement technique. In these systems, 2 stars orbit each other in a plane nearly aligned with our line of sight, causing them to periodically eclipse each other. By measuring the orbital period, the velocities of the stars from their spectral shifts, and the timing and depth of the eclipses, astronomers can determine the physical sizes of the stars and their orbits. Combined with measurements of apparent brightness, this geometric information yields a direct distance estimate that doesn't rely on assumptions about stellar physics. Detached eclipsing binaries in Andromeda have been identified and studied, providing distance measurements accurate to a few percent. These measurements are particularly valuable because they are largely independent of interstellar extinction, metallicity effects, and other complications that affect Cepheid distances. The agreement between distances from eclipsing binaries and those from Cepheids provides strong validation of our distance scale. The study of variable stars in Andromeda extends beyond distance measurements to fundamental questions in stellar astrophysics. The precise period luminosity-color relations observed for thousands of Cepheids provide tests of stellar pulsation theory and evolution models. Discrepancies between predictions and observations drive refinements in our understanding of stellar structure, convection, mass loss, and other physical processes. Andromeda also hosts more exotic variable stars. Long-period variables, red giant stars that vary over many months or years, have been identified in large numbers. These stars are in late stages of evolution, losing mass through strong stellar winds, and their variability reflects complex interactions between pulsation, convection, and mass loss. The study of these variables in Andromeda provides insights into stellar evolution and the chemical enrichment of the galaxy, as these evolved stars return processed material to the interstellar medium. Novae, sudden brightenings caused by thermonuclear runaways on the surfaces of white dwarfs accreting matter from companion stars, occur regularly in Andromeda. Observations have detected dozens of novae over the years, their sudden appearances making them relatively easy to identify. The frequency of novae in Andromeda provides information about the population of white dwarfs and close binary systems, while individual nova light curves and spectra reveal details of the thermonuclear explosions. Even more dramatic are supernovae, the catastrophic explosions that mark the deaths of massive stars or the destruction of white dwarfs. While supernovae are rare, occurring perhaps once or twice per century in a galaxy like Andromeda, they are so luminous that they briefly rival the entire galaxy in brightness. No supernova has been definitively observed in Andromeda in modern times with certainty, though historical records may contain accounts of past events. The variable star population of Andromeda continues to be surveyed with ever-improving completeness and precision. Modern surveys employ automated telescopes and sophisticated image analysis algorithms to detect and characterize variables. These surveys have expanded the known population from hundreds to hundreds of thousands of variable stars, creating vast databases that support statistical studies of stellar populations and galaxy structure. Time domain astronomy, the study of how celestial objects change over time, has emerged as a major frontier, and Andromeda serves as a prime target. Continuous monitoring reveals not just periodic variables, but transient events like novae, unusual eclipsing systems, stellar flares, and other phenomena that occur on timescales from seconds to years. Each discovery adds to our understanding of the diverse stellar population and the physical processes operating in Andromeda. The future promises even more exciting developments. Large-scale surveys will monitor Andromeda nightly, building up complete light curves for millions of stars. Machine learning algorithms will classify these variables automatically, identifying rare and unusual systems for detailed follow-up. Space-based missions will observe in ultraviolet and infrared wavelengths inaccessible from the ground, revealing variable stars invisible in optical light. The story of variable stars in Andromeda intertwines technological capability with scientific discovery. Each advance in telescope size, detector sensitivity, and data analysis techniques has revealed new populations of variables and enabled more precise measurements. From Edwin Hubble's pioneering work with photographic plates to today's digital surveys, the study of variable stars has expanded from a handful of Cepheids to a vast census of pulsating, eclipsing, erupting, and exploding stars that illuminate Andromeda's nature and serve as stepping stones to the cosmic distance scale. Globular clusters encircling Andromeda. Like a swarm of ancient beacons, approximately 450 to 500 globular clusters orbit the galaxy, each containing hundreds of thousands to millions of stars bound together in dense, roughly spherical configurations. These clusters represent some of the oldest structures in Andromeda, formed in the early universe and preserved largely intact over billions of years. Their study provides crucial insights into Andromeda's formation, the processes of star formation in the early universe, and the fundamental properties of stellar populations. Globular clusters differ dramatically from the open star clusters found in galactic disks. While open clusters contain perhaps hundreds to thousands of stars and disperse over tens to hundreds of millions of years, globular clusters are much more massive, much more tightly bound, and incredibly long-lived. The densest globular clusters pack hundreds of thousands of stars into regions just tens of light years across, creating stellar densities millions of times greater than in the Sun's neighborhood. Andromeda hosts an estimated 450 to 500 globular clusters, somewhat more than the Milky Way's approximately 150 to 200. This difference may reflect Andromeda's larger mass and more complex merger history, though the exact reasons remain a subject of study. The clusters orbit through Andromeda's halo, following elongated paths that carry them from the outer reaches through the inner galaxy and back out again, their orbits shaped by the gravitational potential of the galaxy's dark matter halo. The spatial distribution of Andromeda's globular clusters follows interesting patterns. The clusters are not uniformly distributed, but show concentrations and streams that hint at the galaxy's assembly history. Some clusters appear to be associated with stellar streams in the halo, suggesting they may have been brought into Andromeda as satellites of smaller galaxies that were subsequently tidally disrupted. Other clusters show no such associations and may have formed early in Andromeda's history as part of the galaxy itself. Observationally, Andromeda's globular clusters appear as faint, fuzzy spots in deep images, their individual stars generally too faint and crowded to resolve from Earth-based telescopes. The Hubble Space Telescope has obtained spectacular images of some Andromeda globular clusters, resolving their brightest stars and revealing their detailed structure. These observations show that Andromeda's globulars resemble those in our own galaxy, dense concentrations of ancient red and yellow stars with characteristic color magnitude diagrams indicating ages of 10 billion years or more. The metallicity distribution of Andromeda's globular clusters reveals a complex formation history. Like in the Milky Way, Andromeda's globulars show a bimodal distribution. They fall into two groups, one metal-poor and one more metal-rich. The metal-poor clusters, with iron abundances just a few % of the solar value, likely formed very early in Andromeda's history, when the galaxy was relatively unenriched. The metal-rich clusters, with higher abundances, may have formed later or in different environments. This metallicity dichotomy has generated considerable debate about its origin. One scenario suggests that metal-poor clusters formed during the initial collapse and assembly of Andromeda, while metal-rich clusters formed later in more enriched gas. An alternative view holds that many metal-rich clusters were brought into Andromeda through the accretion of dwarf galaxies, each of which had formed its own population of clusters. Evidence exists for both scenarios, suggesting that Andromeda's globular cluster system built up through multiple channels. The kinematics of globular clusters, their motions through space, provide additional clues about their origins. Clusters that formed early in Andromeda's history should orbit in relatively random orientations, reflecting the chaotic conditions of early assembly. Clusters brought in through mergers might show more coherent motions, orbiting in particular planes or directions related to the orbital properties of their progenitor galaxies. Observations have indeed revealed kinematic substructures in Andromeda's globular cluster system, supporting the idea of multiple formation channels. Some of Andromeda's globular clusters show unusual properties that have attracted particular attention. A few clusters appear to have multiple stellar populations, with stars of different ages or chemical compositions coexisting in the same cluster. This finding challenges the traditional view of globular clusters as simple stellar populations formed in a single burst. Instead, these observations suggest that at least some globular clusters experienced multiple episodes of star formation, possibly due to the cluster retaining some gas after its initial formation. The most massive globular clusters in Andromeda rival small dwarf galaxies in stellar mass. These objects, containing millions of solar masses worth of stars, may represent the stripped cores of dwarf galaxies that fell into Andromeda and were tidally disrupted. Their high masses and central densities have allowed them to survive, while their parent galaxies were torn apart. The study of these massive clusters provides insights into the processes that build up large galaxies through hierarchical assembly. The brightest globular cluster in Andromeda, and indeed in the entire local group, is Mile 2, also known as Globular 1 or G1. With an apparent magnitude of 13.8, this cluster is visible in large amateur telescopes, though it appears as merely a faint, slightly fuzzy star. G1 contains several million stars and is about twice as luminous as Omega Centauri, the brightest globular cluster in the Milky Way. Located approximately 130,000 light-years from Andromeda's center, G1 has unusual properties, including multiple stellar populations and a structure more massive than typical globulars. Some astronomers suggest it may be the remnant core of a dwarf galaxy consumed by Andromeda in the distant past. Another notable cluster, B023 G078, appears to harbor an intermediate mass black hole at its center, a black hole of approximately 100,000 solar masses. This discovery, if confirmed, provides important evidence for this elusive category of black holes, which fall between stellar mass black holes, formed from individual stars, and supermassive black holes found in galaxy centers. Understanding how intermediate mass black holes form and evolve could shed light on how supermassive black holes grew to their enormous sizes. Andromeda also hosts extended clusters, systems intermediate in properties between globular clusters and dwarf galaxies. These objects have sizes larger than typical globular clusters, but masses that place them in the cluster rather than galaxy regime. Their nature and origin remain subjects of active research. Some may be faint dwarf galaxies in the process of being tidally disrupted. Others might represent a distinct population of clusters formed under different conditions than typical globulars. The detailed study of individual stars in Andromeda's globular clusters remains challenging due to the galaxy's distance, but the brightest stars can be observed spectroscopically to determine chemical abundances. These measurements have revealed detailed chemical patterns, including variations in elements like carbon, nitrogen, and oxygen that provide clues about the nuclear reactions and mixing processes operating in the stars. Some clusters show star-to-star variations in these light elements, possibly reflecting pollution by an earlier generation of stars or complex mixing during star formation. Globular clusters serve as test beds for stellar evolution and dynamics. The high stellar densities lead to frequent gravitational interactions between stars, occasionally resulting in close-turn encounters or even collisions. These interactions can produce exotic objects like blue straggler stars, stars that appear younger and bluer than they should given the cluster's age, likely formed through stellar mergers or mass transfer in binary systems. Andromeda's globular clusters undoubtedly host populations of these unusual stars, though detecting them requires high-resolution observations. The future study of Andromeda's globular clusters will benefit from next-generation telescopes. The James Webb Space Telescope and future extremely large ground-based telescopes will resolve individual stars in more clusters and extend observations to fainter magnitudes, providing complete color magnitude diagrams and enabling more precise age and metallicity determinations. These observations will better constrain when and how the clusters formed and how they relate to Andromeda's overall assembly history. The comparison between Andromeda's globular cluster system and those of other galaxies provides broader context. Galaxies that have experienced major mergers tend to have more complex globular cluster systems with multiple populations and kinematic substructures. Galaxies that formed more quiescently tend to have simpler systems. Andromeda's cluster system, with its mix of metal-poor and metal-rich populations and its kinematic substructures, suggests a moderately complex formation history, involving both in situ formation and accretion. Globular clusters also serve as dynamical tracers of Andromeda's gravitational potential. By measuring the positions and velocities of many clusters and modeling their orbits, astronomers can constrain the distribution of mass in Andromeda, including the dark matter halo. The clusters orbit through regions far from the visible galaxy where dark matter dominates, making them particularly useful for probing the outer halo's mass distribution. The ancient age of globular clusters makes them witnesses to cosmic history. They formed when the universe was just a few billion years old, emerging from gas clouds in the early stages of galaxy assembly. The stars in these clusters have survived for most of cosmic history, carrying in their atmospheres and interiors records of the conditions and composition of the early universe. By studying these ancient stellar populations in Andromeda, we glimpse not just the history of this particular galaxy, but broader patterns of how structure emerged and evolved in the early universe. The globular cluster system of Andromeda thus provides multiple windows into astrophysics: stellar evolution, stellar dynamics, chemical enrichment, galaxy formation, dark matter distribution, and cosmic history. Each cluster is a complex gravitational system, a swarm of ancient stars that have orbited together for billions of years, surviving the chaotic violence of Andromeda's assembly. Together, they form a halo of ancient lights that trace the galaxy's history and illuminate the processes that shaped it. Closing, as we drift toward the end of this cosmic journey, we find ourselves transformed by the knowledge we've gathered. 100 facts about a galaxy that shimmers in our night sky, a spiral of 1 trillion stars racing toward us through the void. Andromeda, discovered as a small cloud by a Persian astronomer more than 1,000 years ago, revealed as an island universe by Edwin Hubble a century past, continues to challenge and inspire us with each new observation. This galaxy teaches us about the birth of stars in swirling spiral arms, about the patient accumulation of heavy elements through countless generations of stellar death and rebirth, about the invisible scaffolding of dark matter that holds cosmic structure together. It shows us the scars of ancient collisions written in stellar streams and warped disks, the dense concentrations of ancient stars in globular clusters that have witnessed most of cosmic history, and the sleeping giant, a supermassive black hole, waiting at its heart. Most remarkably, Andromeda connects to our own cosmic future, whether in 4 billion years or 8, whether through dramatic collision or close encounter. Our Milky Way and this neighboring spiral are gravitationally bound together, their shared future already written in the invisible ink of space-time curvature. The galaxies we see today, beautiful and distinct, may one day merge into something new, a reminder that even structures spanning hundreds of thousands of light years and containing trillions of stars are not permanent, but rather temporary configurations in the endless cosmic dance of matter and energy. When you look up at the constellation Andromeda on a dark autumn night and spot that faint smudge of distant light, you're seeing photons that began their journey 2.5 million years ago when our ancestors were just learning to craft stone tools. You're glimpsing a structure so vast that light takes 220,000 years to traverse it, yet so relatively close that we can study individual stars within its spiral arms. You're witnessing a cosmic companion, a galactic mirror that helps us understand our own place in the universe. The story of Andromeda is far from complete. Each new telescope, each new survey, each new technique reveals fresh details and poses new questions. Future observations will map its dark matter distribution with greater precision, trace the orbits of millions of stars, identify planets around its suns, and monitor the slow cosmic ballet as it draws closer to our own galaxy. The next century of Andromeda research promises discoveries we cannot yet imagine, built on the foundation of knowledge painstakingly assembled over a millennium of human curiosity. If you enjoyed drifting through this exploration of Andromeda's wonders, from its discovery by ancient stargazers to its satellite galaxies, from its spiral arms to its invisible dark matter, from its supermassive black hole to its ancient globular clusters, consider subscribing to journey through more cosmic landscapes where science meets serenity, where the immense and ancient universe unfolds in gentle, thoughtful detail. Until we meet again under the stars, keep looking up, keep wondering, and remember that we are all travelers through the cosmos, connected by gravity and light to spirals of stars millions of light years away. Sweet dreams and clear skies.